In this video, I want to talk about piecewise functions. Sometimes you'll hear folks call them piecewise defined functions, and they are exactly what they say they are. They're a function where different ranges of the domain, different x values, have different rules. They're functions that come in different pieces. So here I have a piecewise defined function where f of x is equal to 2 for all the x's less than minus 1, x plus 3 if x is between minus 1 and 2, including minus 1 and 2 with those equals in there. And then finally, if I have an x value that's larger than 2, I'm just going to get out minus 1. So I have several examples here where I want to evaluate this function. And so I'm supposed to find f of minus 2, and the first thing I need to do is say, hey, which piece of the function am I supposed to use? Which range of x do I have? So I look at that minus 2, and well, minus 2 is less than minus 1, so I use that first piece, and I'm just going to get out a 2. F of minus 1.5 here, well, I have another x value that's less than minus 1. I'm going to get out a 2 just using this first piece where, hey, every x is assigned to the value 2. And then finally, I'm asked f of minus 1, and what I realize is that's no longer talking about this piece. I've jumped into the next piece where x is equal to minus 1, and I'm supposed to use the formula x plus 3. Minus 1 plus 3 is 2. I have another x value between minus 1 and 2, so 0 plus 3 is 3. F of 1, 1's still in that interval, so 1 and 3 make 4. F of 2, that's the last piece here of that equal to. I'm definitely using this piece, and I get the number 5, 2 plus 3. And then finally, I have two examples where my x values are larger than 2. F of 3, get out a minus 1. And f of pi, I get out a minus 1. You know, I changed colors a little early there. Wasn't supposed to do that when I changed columns, but when I changed piece of the function, so here I was still an f of 2, and 2 plus 3 is 5. So I have three different pieces, and right now I'm kind of thinking of them sorted into those different colors. All the x's less than minus 1 give me a 2. All of the x's between minus 1 and 2, they give me whatever x plus 3 is. And finally, anything larger than 2 gives me that minus 1. So we've evaluated a piecewise defined function. What I'd like to do now is graph this piecewise defined function. I'm going to do that by using a table of values for each piece. So in this first piece, I'm supposed to have x's that are less than minus 1. So I'm just going to pick some x's. And I'm going to stop at minus 1. And I think some of you might be thinking right now, well, should minus 1 be in that table? Because that says less than, not equal to, right? Minus 1 actually belongs in that next table. And what I'm going to tell you is that we always put the thing in the boundary into our table. Because that's going to tell us where an open circle goes. Right? Wherever I don't have the equal to, I'm going to get those open circles like we've seen in other examples. Where I have the equal to, that's where I'm going to get a filled in circle. So let's go on and fill in this table and start graphing, and I'll tell you a little bit more about that open circle. Well, for all of these, I just get out the number 2, so the function is pretty easy to evaluate. So the function's constant over this interval. So minus 3, 1, 2, 3, up 2, minus 2, 2, and then I claim there's an open circle here. All right, the reason I need that open circle there is because if I thought about something like f of minus 1.1, I get out a 2. Something really close, I get out a 2. And this tells my reader that I get out that positive 2 until I get here at minus 1. The open circle's there because that's where the endpoint is, and that's where something changes. All right, so these values in the boundary where the rule changes, they're either going to get open circles or filled in circles. If there's just a less than or a greater than, we're going to get an open circle. If we have a less than or equal to or a greater than or equal to, we're going to get a filled in circle. So now let's check out that next piece. So I'm going to build a little table of values for it. And I'm just going to pick some x values that belong between minus 1 and 2. And again, I'd use the boundary values no matter what. But this time, because I have those equal to's, I'm going to get a filled in circle. Plug in a minus 1, I get out a 2. Plug in a 0, I get out a 3, and finally a 5. And we saw those values earlier when we were just evaluating. All right, that was an open circle, and it turns out this filled in circle is supposed to go in that same spot. So it's like it completes itself. It tells me these two pieces actually touch each other. All right, and so there's that nice happy piece. And then finally, one more little table of values where I'm supposed to pick values that are larger than -2, but -2 is going to go on my table. Oh, +2, sorry folks. And things larger than 2. And again, that value goes in my table because it's going to tell me where to put an open circle. And again, a very easy thing to evaluate here. For all of these x values, I get out a -1. All right, here's where that open circle is important on this one. Because here I have a filled in circle, here I have an open circle, and I need those to pass the vertical line test. So that point's not on the graph, that point is on the graph, and everything's fine. And so here I have this kind of weird looking piecewise defined function that's constant in two places and increases from -1 until 2. All right, well, I thought we'd graph one more in this video. So I have another piecewise defined function here. We're going to sketch a graph of it. If you wanted to, you could pause the video here and sketch your own graph. All right, well, I'm hoping that you actually pause the video and we're working on your own graph. I'm going to go on and get started on it now. So I have this first piece, and that's a piece for x's between -3 and -1. And again, even though there's not an equal to there, I put it in my table because that's going to tell me where an open circle goes. Well, in between -3 and -1, I always get out a -1. In fact, we could probably just imagine what that looks like without having to draw the table of values, but it's always fine to do that. So -1, -2, -3. Open circle -3, -1, because that -3 doesn't have an equal to on it. All right, so that little part of the graph would look just like that, starting at an open circle, ending at a filled in circle, because I have a less than and then a less than or equal to. Between -1 and 2, my graph is that of x squared plus 1. So I put -1 and +2 in my table because that's where my interval begins and ends. And because there's no equal to on either one, I know these are going to correspond to open circles. I'll just put a 0 in between them, get one more point to graph. And again, I could put more points in there. I could put 1 in there, 1.5 in there. -1 squared is 1, plus 1 is 2. So in that, I get that little shape there. And again, we could always make our graphs better by plotting more points. And finally, I just need one more piece. And I'm plugging these x values into 7 minus x. So I'm just subtracting those x values from 7. So now I have some points to plot. Hey, I landed right there. And so, well, now I realize that was supposed to be an open circle to begin with, but I got lucky because this next part fills in the circle. 2, 5 is on the graph. And that piece continues on because those are for all the x's greater than or equal to 2. All right, so we've graphed 2 piecewise defined functions, and all we have to do is think about each piece individually. Remembering, open circles happen when I have a less than or greater than. Filled in circles happen with greater than or equal to's or less than or equal to's. And we can have these cool places where graphs fill themselves in where I have 2 pieces that touch. All right, that's it for now.